Hey there, we are Unit 3 Lesson 5, Splitting Triangle Sides with Dilation, Part 1. Notice and wonder. So notice and wonder, here we have some midpoints. We're saying that I have triangle ABC, and I have midpoint L, M, and N. And we can see it's the midpoint because these marks, right? Okay, single ticks, that means CL is congruent to LB, triple ticks. BM is congruent to MA, double ticks. AN is congruent to NC. So we can see that those are all congruent. Now, what do we notice? What do we wonder? Right? What do you notice? What do you wonder about this? I wonder what those measurements are. Just wondering. I wonder if AC is parallel to LM, or LN is parallel to AB, or even NM is parallel to BC. I wonder. I wonder if I have congruent triangles, like 1, 2, 3 congruent triangles, and then if I flip this one over, a fourth congruent triangle, because I really do wonder if this is 3 ticks, that's 2, and that's 1. I'm going to give you a hint. You might want to rewind the video and write those things down because they're really important. Okay, all of those wonders are actually true. Let's see if I can write them down for you. But I would still, honestly, rewind and look at, write those things down because all of those things are absolutely true. Let's see. AM is equal to MB. AM. Yeah, those are all true. I don't need to write that one down. We got that one. It's the tick marks, right? There are 4 small triangles, is true. Now I wonder if MN is half as long as BC. MN, yep. Is MN parallel to BC? Are the small triangles congruent? And are the 4 triangles similar to ABC? I wonder. Okay, they're all true. We're going to talk about it today. All right, so dilation or violation. Here's a triangle ABC. Points M and N are the midpoints of the 2 sides, and we see that because of the double tick marks and the single tick marks. So convince yourself that triangle ABC is a dilation of triangle AMN. What is the center of dilation and what is the scale factor? So let's look at it. So I just copied that figure over from our curriculum. I'm going to go ahead and make one. So I'm just going to draw a triangle and we're going to play with it a little bit. So I have a triangle. I'm going to dilate that triangle. What do you think I should dilate it? We're going to dilate it by 2, just see what happens. 2s are really, really easy to work with because I can do math by 2 pretty easily. I can do things by doubling, decently easy. So let's dilate this from center C, a factor of 2. Now, if I look at the original one, I see that AN is congruent to NC. So I'd like to see if that's true. Let's go ahead and measure it. I'm going to measure CD and DD. They're the same. CE and EE prime. And they're the same. So that is a dilation, a factor of 2. All right, I'm going to go back to the notes and see. So here it's a scale factor of 2. I can write that down. Center dilation was A, and the scale factor was 2. And yes, and if we were in the classroom, I would take my compass and just measure AN and NC with circles, and it would work great. Okay, I wonder if I could do that here. Hold on, take a little trip. Just curious if I can do circles. I want my compass circle. There it is. I don't know if it'll let me. Nope. I don't think it'll let me draw. No, bummer. Okay. That's how we would have done it though. Going back to here. Convince your partner that triangle ABC is dilation of AMN with the center and scale factor we found. We did this in GeoGebra just fine. With your partner, check the definition of dilation on your reference chart and make sure you both could convince a skeptic that it is definitely a dilation. It is. We constructed it that way. So, and now convince your partner that segment BC is twice as long as MN. Let's go do that. So BC is twice as long as MN. It looks like it, but I'm not really sure, and I hate to do things by it looks like it because we know that doesn't work. So I'm going to measure it, and again, we could use our compass. I guess we could do, I'm going to show you this really quick, and then I'll go back. So that's a radius, and now I want to that's how I would have done it on paper. I would have I would have used a circle to check the radius, and then I would have copied that to make sure it was the same measurement. But we don't need to do that now. Now we're just going to take a measurement. If I measure DE, it's 2.3, therefore D prime E prime should be 4.6. Woohoo, it worked. Okay, so that doubled. And that means that, I know this one doesn't write very well, but if CD is 2.9, then C prime D prime is 2.9 times 2. Okay, because we're looking at the little triangle compared to the bigger triangle, where this was 2.9 and this is 5.8, which is 2.9 times 2. So everything is doubled. Here, this one is 3.4. Well, this one is 6.8 because it has doubled. That's why this is 2.3 and that is 4.6. Each side of the triangle has doubled when it dilated. Okay, very important. Nope. Convince your partner, we did that. Now prove that BC equals 2MN. We did it just by actually constructing it. See if there's a different way to do that. Let's see. So let's just try to sketch this out really quick. Let me write this down. So here we're going to try two-column proof. We can say that segment AB is twice segment AM, the measurement. Sorry, my phone rang. All right, what we were talking about was AB is twice the length of AM because of the definition of the midpoint. The midpoint cuts something in half, so the lengths are twice, like the length of the big one is twice the length of the small one. All right, so that would be our reasoning. So when we dilate point M, using center A and a scale factor of 2, it takes M to B. Yep. And I can do the same argument for AC. Yep. AC is twice a, oh, I see my mistake. This should be M. Sorry. So AC is twice AN. Same thing. Definition of midpoint. When I dilate point N on center A scale factor of 2, I take N to C. And that's really it, okay, because of the dilation. Awesome. So going that a little bit further now, okay, here is triangle ABC, and then M is 2/3 of the way from A to B. So M is 2/3 of the way from A to B. So basically, if I mark this into thirds, that's how it would look. Oops, I don't know why I did that. So we're a scale factor of 2/3 with a center of A. So what can you say about MN compared to BC? I can say that they are parallel. I can also say the measurement is going to be 2/3 of the measurement of BC because of the scale factor. Okay, what else can we say? I like those things. Parallel, yep, got that. And because it's a dilation at center A, it's going to be parallel. And then MN is 2/3 of BC because dilating a scale factor of 2/3 with center A takes the points, it takes B to M and C to N, and it would just, that the measurements are exact. So when you have a scale factor of 2/3, the measurement of your triangles is going to be reduced, and your new measurement will be 2/3 of the original measurement. Okay, if you want to write down dilations, multiply all distances, all measurements by the scale factor. Okay. Here we have the same thing. This is, it looks like if our original triangle is ABC, then our dilated one is a scale factor of 1/2 because the measurements, actually not 1/2, I'm sorry. That is incorrect. You don't go from 2 to 1. You go from, it's a great example, 3 to 1. Okay, if we're scaling down, we have to do the whole thing. This would be 3.6 to 2. So here I did a scale factor of 1/3 because everything got 1/3 smaller. Okay, where this one is 2/3. It went from here to there, which is a scale factor of 2/3. And here I went from there to there, scale factor of 1/3. It went even smaller. That's it. That was easy. Not easy. It's never easy. That was short, but challenging. Good job.